Okay, thank you for joining us today for a hot topic about climate-resilient nuclear power plants. I'm Nicolas Goreaud. I'm a fellow expert in fluid dynamics in Framatome.
And my name is Daniel Walz. I'm working in Framatome since 20 years and I work for the sales department in Erlangen.
So maybe to begin with, a few words about Framatome, if you do not know us already. Framatome is a French company with a revenue of 4.6 billion. We design, we build, and we service nuclear power plants all around the world. There are more than 20,000 people in the company, and we are located all around the world. Daniel?
So before we start with the actual use cases, later on I want to first give you a short introduction. As you see, the world has been, and especially the IAEA, since the late 1980s discussed the climate change topic. Yeah. First papers are available since the late 1980s. And you see here on the left side the two latest ones. That's the 2022 and 2024 paper. It's really exhaustive. And this guidelines has then been taken by many organizations and also countries and included some of them into their rules, regulations and standards. You see, for example, ENSI in Switzerland, the ASN in France, STUC and so on. So this is, let's say, floated down from the IAEA to the national rules and regulations. If we go to that paper, there is being discussed this map. So you see indeed the yellow spots are inland near lake sites, the red one are river sites and the blue one are coast sites. And what is being discussed is the vulnerability of these sites, and what is identified as the most severe cases is aridity and drought for and heat wave for the nuclear power plants. I would say in global perspective, I mean, it's clear if we have higher outside temperatures, you will have a loss of efficiency. There is a paper you can check and it says about 1 degree increase of the cold end will be efficiency loss of about 0.5%, and during trough and heat wave even more, up to 2%. Nevertheless, these losses due to heat are not at the moment not that bad. In the IAEA paper it is shown that these losses are like a third only compared to other interrupted grid losses. We have from Framatome conducted a lot of analysis because some of the hazards like tornadoes, large-scale wildfires, extreme wind, more hot and cold days and higher peak temperatures on the positive as well as the negative side has been included in the collection of the potential incidents. All analysis what Framatome have conducted so far does not endanger any safety goal of our nuclear power plants. Nevertheless, we recommend that all operators should check on an individual basis that this changing and the changing conditions and therefore the added scenarios had been included properly. This is in line with the IAEA statement that the nuclear sector is at the moment well prepared for this IPCC. This is the international board which has, let's say, put the perspective of this 2-degree increase over the next decades, and the nuclear power plants are good prepared. This is kind of introduction, and we show you now some use cases, what we have done within the analysis of our plants with regard to that climate change topic.
Okay, so in terms of solutions, we have three main stages of solutions that we can propose to our customers. The first stage is what we call advanced modeling. What modeling does is that it brings you knowledge of the consequences of the climate change on what's happening inside your nuclear power plants. The second thing it brings is a set of margins. So you can use these margins in order to justify, to limit the amount of work that you need to make in order to comply with the regulations. It might be enough, but it might not be enough. So in this case, the second stage of solutions that we propose is hardware performance upgrade. So we can work on your hardware to increase its performance. So that means decrease the heat losses, increase the efficiency of the cooling system, of the venting, and so on. And sometimes, even this performance upgrade is not enough. So we can propose you new dedicated solutions adapted to climate change. That can be more of what you already have, but that can also be innovative solutions that change a little bit from what you have. And we will present you two use cases of advanced modeling, and then Daniel will present you two use cases of new dedicated solutions. So let's go to the use cases now. The first one is related to normal operation. In normal operation, you need to perform outage of your power plant. When you want to perform an outage, you need to get inside the building, and one of the first operations that you want to make is to reactivate the polar crane. The polar crane is located at the very top of the building, and it's the hottest spot of the building. And there is a norm that fixes a duration limit for the work in such condition. The duration limit depends on a dry temperature, on the temperature of structure, on the hygrometry, and of the velocity of air where the workers are actually doing things. What we see with our customer is that as the climate is getting warmer, you have an aggravation of the temperature, and so the duration limit for the work on the polar crane is limited, and people need to wait before they can actually work there. And it's on the critical path for the outage. So we've been working with our customer, EDF, the solution to this problem, and we activated the first stage, which was advanced modeling. So we used the modeling strategy to better understand why it was so hot at the very top of the building. And we used it also to quantify pros and cons of different strategies that we could use in order to cool down the temperature inside the building. And these strategies might be, you can stop some venting system if they are not useful. You can restart, or you can increase the flow rate of other venting systems. You can choose to open some communications between rooms inside the building, or you can choose to, the contrary, shut down doors and be sure that there is no communication. We had a pragmatical approach. Then we started with a very simple model that we call a multi-0D. That means an analysis performed only on 3 volumes. That's what you can see here, 3 simple volumes. And this was backed up by a simple 2D CFD analysis of the whole building. We could have triggered a 3D model, but in this case it was not useful, so we didn't do it. We did it for a more complicated case that I will present just afterward. And the idea here is that we are working on finding an optimum between the cost of the study and the complexity of what we are actually studying. In terms of results, we were quite satisfied. We had good agreement between what the model yielded, predicted in terms of temperature, and what was actually measured inside the building. It enabled us to accurately understand what was going on inside the building, what was the root for the very high temperature that we had at the very top of the building. And we could propose several, I call them design evolution, but it was rather operating evolution. That means different strategies for managing the venting system of the building. We could use our model in order to assess the efficiency of all of these changes before actually implementing them inside the building. In the end, EDF gained 48 hours on its outage planning, and we could identify real solutions versus, I would say, intuitive solutions, because sometimes intuition is very misleading, and you need to actually assess precisely what's going on and what's the consequences of your choices. So now we have this capacity of delivering robust models that are actually deployable on site if you want. If you want to test the consequences of your management strategy. My second use case is now in the world of accidental analysis. In the safety analysis of plants, you have to consider the possibility that you might lose your heatsink. So in that case, you have no way of cooling down the inside of the building. Nevertheless, you need to get back to a safe state for the plant. And to do so, you rely on electronical equipment and safety systems that are located inside the buildings. So that means they will be experiencing a heat up and high temperature. There is what we call a qualification temperature. That means that all these equipment are qualified to operate under high temperature, but you must demonstrate that they will not go above this temperature during the operation. And EDF is in charge of this qualification. Due to global warming, the external temperature are rising, so there is a risk for increased temperature inside the building. So we helped EDF to demonstrate that the temperature inside the building was remaining below the qualification temperature. So what we did is that we used this time a very detailed modeling of the whole building. We had an explicit representation of all the heat dissipation sources inside the building. We had a detailed representation of all the rooms of the buildings, a detailed representation of all the venting system, and of all the main components. You can see here a representation of the reactor pressure vessel. We had the same for the coolant pumps and so on. And we were quite serene in doing this in 3D because we have validated codes, and we could also benchmark our results against available temperature measurements inside the building. So in terms of results now, you have here a plot of the assessment of temperature evolution inside the building during the accident. So what you can see is that the modeling has shown that it was very important to stop the reactor coolant pump as soon as possible because it's a very powerful equipment. It dissipates a lot of heat, and you want to stop them as soon as it's reasonable. Then the second thing that we demonstrate is that there is a thermal stratification inside the building. All these curves are plotted as a function of temperature. So you can see also on this graph here, it remains cool at the bottom of the building, while it gets hot faster at the top of the building. And this stratification is impacted by the strategy that you take in operating your venting system inside the building. So depending on where your equipment is located, you have interest either to increase the flow rate or to completely stop the venting inside the building. So based on this 3D model, we could justify that it was possible to find a venting strategy that did not require to change anything in the plant, and that you can cope with warmer outside temperature without putting the safety of the plant at risk. So we could demonstrate that it's not required to do anything in the plant to cope with the change in temperature.
I think I take this one. So this is our use case number 3. We call it the thermal convection flow stopper. What is the issue is you have big lines, hot lines, you have insulation, and we found out the issue that there will be chimneys and let's say heat losses between the insulation and the piping that comes out at a certain point and is giving a high heat load to different rooms. We figured this out when we have the fatigue monitoring system. They measured around the pipes, and we had between several sensors differences in temperature between 8 to 18 degrees. So this comes through the heat is sucked in somewhere, is like had a chimney effect and is put out somewhere else. What is our solution? Our solution is the thermal convection flow stopper. So we put these stoppers inside the between the insulation and the pipe, and we are making like little compartments of pipe, and it was then not possible that the air is moving alongside the pipes and is and completely this chimney effect was not seen again. So we did that in our nuclear power plants, especially in Olkiluoto 3. We have installed that, and we have measured and seen that this effect is no longer there. So you could either like work with the HVAC system, or you could, let's say, reduce the heat at where it is being generated. And this was the idea here. And we totally avoid this heat flow through the gaps of the insulation and the pipes. So main benefit for the customer is that it is easily to add on. You can easily install it, remove it, also during outages, and what we see is no longer incorrect readings of pipe sensors. Yeah? And I brought something new with me. It is developed the last year, and the issue is loss of HVAC in rooms where you have more and more heat load due to the digital INC. If you change your INC or if you have new INC, and you need maybe to prove that your INC equipment is not to be overheated, and you have a very long grace period to undertake some measures if it occurs. What have we done? We have installed a rack in the room which has in this phase change material you all know from the pocket heaters. If you click it, it warms up, and we use this effect the other way around. And in case of HVAC, HVAC loss, this cabinet will open flaps on the bottom side and on the upper side, and then the hot air which is generated from the cabinet is sucked in at the top and is released at the bottom, and we could show that we could extend the grace period for the loss of HVAC for up to 6 hours. We have been patented this, and it is now this year being tested very exhaustively, and hopefully we could then install it in our new builds and also in retrofits for our existing plants. The benefit for the customer is to gain more grace period in case of loss of HVAC to fix the malfunction INC or whatever this causes. Yeah, and have a more reliable, let's say, INC function. What we can do, we have now already the models to analyze how much is needed of this phase change material, and we have also the possibility to retrofit it easy to any kind of plant. We got also some contacts for data centers. They obviously have the same issue somewhere. Yeah. Okay.
Okay, so a short conclusion now. The key messages here is that climate change will stress NPP operation, and it's not, I wouldn't say, a fate that you must make works inside your NPPs to adapt. At first, you can use advanced modeling to try to justify as is. That means to justify that you do not need to make any work inside the NPP to cope with the new temperature. But it's not sure that it's enough, and you might have to either improve the performance of your hardware or add new one. And in this case, at Framatome, we can deliver adapted hardware solutions that are fitted to your needs. But what is important to understand is that there is no single magic solution to the problem. It's more a tailor-made adaptation of what you have. And so we encourage you to reach out to us, and we can discuss about your own problem and see what is the best solution for your case. So thank you, and stay connected with us. We can meet at our booth on F054. Thank you very much for your attention.